Hi, today I'm going to show you how to do this particular AS exam question. It's from Unit 2. It's question 1 on the paper. It's about lasers, although there's some work on photons in here as well. And we have a diagram here showing us a 4-tier laser system and the energy difference between two of these levels. And the first thing it wants me to do is calculate the wavelength of radiation as an electron drops, or emitted as an electron drops from U to L. So the first thing I need to do is find out the difference in energy between these two. So I'm going to do 0.820 minus 0.051. And that's going to give me 0.769 electron volts. Now, if I want to calculate a wavelength, I'm going to have to use some equations that require me to have this energy in joules. So I'm going to convert it into joules by doing 0.769 times 1.6 times 10 to the minus 19. And that's working on timesing it by the charge basically on an electron, and that will bring it into joules for me. And that's going to give me 1.2304 times 10 to the minus 19 joules. And then I'm going to do over here, I'm going to just do a little bit of work with the formula that I know. So I know that E equals HF, that's on my formula sheet. And I also know that V equals F lambda. So if I rearrange so that F is on its own, I'm going to get F equals V over lambda. So I can put that in here. So V over lambda. And if I'm trying to get wavelength on its own from the question, I need to swap these across here. So therefore, wavelength is equal to HV over the energy change. So that energy change is this energy change here. So if I fill that all in, H is Planck's constant. So that's going to be 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Now you're expected to remember in an exam setting that the speed of light is 3 times 10 to the 8. And then it's all going over this number from up here, so 1.2304 times 10 to the minus 19. I would round this if it was a final answer, but it isn't. So I'm going to leave it whole as I bring it across. That's going to give me an answer of 1.2. No, it's not, sorry. It's going to be an answer of 1.62 times 10 to the minus 6 meters. And the next section of the question is a bit more writing heavy, and it wants me to explain how stimulated emission enables amplification of the infrared radiation of this wavelength. So I'm going to say, so we're looking at as a photon comes this way, it will stimulate a drop in the electrons from U all the way back down to L, emitting light as it does so. So we'll just write that down. So as the correct wavelength passes, it stimulates the drop of an electron from U to L. This emits a matching photon, which will be in phase. Okay, so in phase meaning, of course, that it has the same wavelength, the same frequency, and it's traveling in the same direction, and all those things that come with that. So, explain the advantage of a 4-level laser system over a 3-level laser system. So, just come back to the diagram again. This section here is involved in a 3-tier system. So this is the difference here. This level L is the fourth level that they're talking about within this question. And one thing we know is that this L here, the electrons will exist in it for a really short space of time. Okay, so level L will only hold electrons for a short time, and that makes it easier to create a population inversion. Okay, I'll slide back up again. So what we don't want is anything getting in the way of this drop here. So we're going to pump electrons from ground state up to P. They'll then fall into U. That's your standard three-tier system. And then they will drop into L. But they won't hang around here. They'll drop down. We want as many electrons up in U ready for arriving stimulating photons as possible. So we want to keep this shell full, and we want this one empty, causing no barriers to the drop. I hope you found that useful, and I'll do some more videos later. Thank you.